TU.podcast.
While sitting, I didn't want to stay in bed, so you would miss a lecture. Okay, what did we do last time? Please, 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 guys, girls. Now, last Friday morning, not all of you were here, I think. It was a very nice and quiet lecture, and actually that's the way I prefer it and the way some of your more serious colleagues prefer it. I got even some complaints with regard to the talking that goes on throughout the lecture and that people have trouble concentrating. Actually, please, if you want to talk, it's perfectly fine, but do it outside. In favor to help your colleagues, students, and me, please. Okay, so last time we started out with measurement of flow speeds, incompressible flows, compressible flows. We discussed the manometer, the pitot tube, which measures total pressure, and a static pitot tube, which actually measures the pressure difference. It can measure total pressures as well as static pressures. And then we derived the second form of isentropic relations, and that are these three. And these are quite important to remember. We derived them from conservation of mass and Euler equations, so conservation of momentum. And what they are, and we use this first form of isentropic flow relations, and what they are, they're just sort of a rewriting of these equations, but they're quite handy, because what they do is they relate temperature ratios to the Mach number. So once you know a temperature ratio, you know the Mach number. And please be aware, it's not just a temperature ratio, but the zero is really total conditions, where the speed is zero. So T0 in reservoir or stagnation temperature over T1, temperature at a certain point, is 1 plus gamma minus 1 over 2 Mach squared in that certain point. So once you know the total temperature and the temperature at a point, you can derive the Mach number and the other way around. And of course, if you have this one and you use the first form of isentropic flow relations, you can directly find the pressure ratio and the density ratio as such. Okay, and then we did this, and then we were here, so the example problem, I didn't have time to do an example problem with you, so now I'm going to do it now. Please be aware that most examples, almost all examples I do here are just written in the book, so they are Anderson examples, so the whole answer and derivation you can read in your book. So this is example 435 from Anderson, and it concerns a combustion chamber of a rocket engine where kerosene and oxygen are burned, resulting in a high-pressure gas mixture which is hot in the combustion chamber. And the following conditions are given. T0, 3144 Kelvin, P0, 20 atmosphere, R, 378, and gamma, 1.26. And please note that now we have a different R and a different gamma than for standard air conditions. Pressure at the exit is 1 atmosphere, and the throat area, so the smallest cross-section, is 0.1 meters squared. Oops, rocket. Assuming isentropic flow through the rocket nozzle, calculate the velocity at the exit and the mass flow through the nozzle. Okay, so let's start with the velocity at the exit. Any ideas what relations we can use? Velocity at the exit. Pressure ratio, right? So pressure ratio as a function of what? The second form, right? So we can do the pressure ratio, so P0 over P1 is a function of the Mach number, right? We can use that. Because we do have the pressure at the exit, we have the zero pressure, so we have the ratio. Then we find the Mach number, and what do we need in addition if we have the Mach number to find the speed? Speed of sound, yes. And what relation can we then use? Square root gamma RT, right? And let's suppose this is the exit, right? We're looking at the exit. So we do have the pressure at the exit. So we find the Mach number at the exit, A at the exit. We need the temperature at the exit. Do we have the temperature? No. Can we find the temperature? Yes? Equation of states is an option, but we don't have the density either, right? So what relation can we use to find T at the exit? P0, P1, and T0, indeed. So the relation, the first form of isentropic flow relations, right? Oops, so this is the first form of isentropic flow relations. Then we find TE. Then we can use TE in there. And okay, let's do it. I prepared it slightly differently because you can also, there's another way you can do it. Namely, instead of using this ratio, so instead of using this form, of course you can use the temperature ratio as well, right? Because if you do through this, you find the T exit. And you could also have used the T0 over TE here. You find the same answer, okay? Yeah? Shall I do it or shall we leave it? Do it. Okay, let's start. So P0, let's first find TE. So PE over P0, first form of the isentropic flow relations, is equal to TE over T0 to the power gamma over gamma minus 1. So we're looking for TE. So TE is equal to PE over P0. And we have to then take this to the power gamma minus 1 over gamma to get rid of the power, right? Because if we do this to the power gamma minus 1 over gamma, we have here, at this location, we have then to the power 1. And then here we get to the power gamma minus 1 over gamma times T0. So TE is equal to, T0 was given 3,144. And then the pressure ratio, yes, no. So P0, 20 atmosphere, and at the exit 1 atmosphere. So P exit 1, P0, 20, and gamma, does anyone remember gamma? 1.26, eh? Yes, perfect. It was given. 1.26 minus 1 over 1.26. And then we find the temperature at the exit being 1694 Kelvin. Okay, so step 1. Now we can compute the speed of sound. Square root of gamma RTE. Gamma is 1.26. R was given to be 378. And the exit temperature we just computed is 1694 square root. So then we find 889.2 meters per second for the speed of sound. Now I'll do it the slightly easier way. So I compute the Mach number from the second form of isentropic flow relations, namely T0 over TE is 1 plus gamma minus 1 over 2 Mach at the exit squared. So Mach at the exit squared is equal to T0 over TE. Then I take this one to the other side, so minus 1. And I multiply by 2 over gamma minus 1. Yeah? So then I find that Mach at the exit is T0 was 3144. T exit we computed 1694 minus 1 times 2 over 1.26 minus 1, and then we take the square root to find the Mach number, and then we have the Mach number 2.566. Yeah, last step easy. So Mach number is equal to V at the exit over A at the exit. So A exit is Mach number, sorry, we're looking for VE. This is so, I much more prefer a blackboard. Okay, so we're looking for VE, so that is Mach number times speed of sound, so that's 2.566 times 898.2, and that is equal to 2,305 meters per second. Yeah? And please be aware, there are probably different ways to solve this using different forms of the equations, but this is the correct answer. Questions? So what did we do? First, compute the T exit from the first law, first form of isentropic flow relations, compute the speed of sound, and then with the second form, compute the Mach number, and then we're there. Yeah? So that solves A. Now B, the mass flow through the nozzle. Mass flow. What's the definition of mass flow? Rho V times A. Rho VA. Great. So Rho AV. Any suggestions where we do this? It is constant, so it doesn't matter, right? Mass flow at any cross-section is the same. Any ideas where we can do this? Yes? Exit. We just computed the velocity at the exit, so that is tempting. But do we have the... We might find rho, we might find v, but do we have the cross-section of the exit? No. We only have one area, right? So the area is really hampering this, so you have no choice but to choose the throat. Yeah? So let's do this at the throat. So mass flow at the throat, stars. Okay, so we're looking for rho star, A star we have, and V star. Any ideas? Rho star. Density at the throat. What do we know about the throat? Mach is equal to 1. Very good. So it might be good to use the second form of the isentropic flow relations to find conditions at the throat. Any ideas? Yes. Question, why is the Mach equals to 1? Yeah, it's a bit hard to explain. I will, I think later I have a few slides on that. So if you put in the equations, you can see that you can see a relation between areas and velocities. I'll do later. But if you do the computations, you will find it. So Mach is 1 in the throat, always. The smallest cross-section if you have a supersonic nozzle. And this rocket engine, it looks something like this. With an exit and a very strong contraction ratio. Flow through this combustion chamber. Yeah? So, rho. Who gives me rho? No? So we start with V then? We have T0. Okay. And what do we have otherwise? No. Will not give us, because we have T0, but we need another T, and T exit will not help us because it will give us conditions at the exit. Please think of this. Come on, it's not so hard. Look at this. Now it's the other way around. So earlier we had the temperature and the temperature, but now we have a T0 and a Mach number, right? We know that the Mach number in the throat is 1. So we can find the temperature. Does that help? Yeah, we can find the pressure and the density. Yes, perfect. So let's do that. So the density we have here. So we can find the density from this one. So we have T0, we have Mach at the throat. So we can use the second form of isentropic flow relations. Rho 0 over rho star is a function of Mach star, and that gives us rho star. Yeah? V star. Any ideas on the velocity in the throat? Yes? Find the Mach number throat, V star over A star. So the velocity in the throat is the Mach number in the throat we know, times the speed of sound in the throat. So that transmits the problem to finding the speed of sound. What do we need for the speed of sound? Temperature. Perfect. How do we find the temperature in the throat? Mach number and T0. Indeed, another form of the isentropic flow relations. T0 over T star is 1 plus gamma minus 1 over 2 Mach star squared. Yeah? So now we're there, right? We find the temperature from this one. We find A star. So we have the velocity. Then we can find also the density with isentropic flow relations, and we're there. Yeah? So the crucial thing to realize here is that you don't have much conditions at the throat. We do have the area, so we have no choice but to compute the mass flow through the throat, the only place where we have the area given. But we do have information on the Mach number, and that can give us a lot of information on the temperature, pressures, and densities, okay? Okay, so let's start here. So T0 over T star is equal to 1 plus gamma minus 1 over 2 M star squared. M star is 1 in the throat. Gamma is still 1.26, so times 1 squared. So that gives us, this is equal to 1.13. So T star is equal to T0 over 1.13. So that is then, I can't read my writing, 278.2.3, I think. I hope it's correct. 2,782.3 Kelvin. Okay, temperature. So now we can find the speed of sound very easily. Same trick, gamma RT. Gamma is still 1.26 in our case. R was 378. Temperature we just computed. Square root. So that gives us a speed of sound of 1151 meters per second. And since Mach is 1, this is also V star, right? Because Mach is 1 in the throat. So that gives us V star. Now we only need rho star. And for that we're going to use this one. You could also do the P, of course. Use this, the pressure, and then the equation of state, but that's 2 steps. So rho 0 over rho star is equal to 1 plus gamma minus 1 over 2 mag star squared to the power 1 over gamma minus 1. Yeah? So 1 plus 1.26 minus 1 over 2, 1 squared to the power 1 over 0.26. And I don't have this because I chose the other way to do it. Can anybody type this in? What the answer is of this? And then rho star is equal to rho 0 divided by that. And I have rho star. This ratio? Anyone with a calculator? I'm a bit. 1.6? Okay. 5538? Well, 0, 0. Okay, perfect. 1.6. So the ratio of the total density over the throat, density in the throat is 1.6, so we find the density in the throat. So what we now need to do, what were we doing? We were computing the mass flow, so we now have to do rho star, A star, V star. Rho star we have here. V star we have here. And A star I don't remember, but that was given 0.1. So last step, mass flow is rho star, A star, V star is equal to 1.062 times 0.1 times 1151, and that gives us 122 kilograms per second. Wow, that's a lot. 120.2 kilograms per second go actually through this rocket nozzle. So, a lot of power. Any questions about this? No? Does anybody have it? Or do I need to have the first slide, one slide back? Yeah? Okay. Just a few more minutes. Yeah? Okay. Let's continue. A few considerations on compressible flows. I brought a picture with me of one of our supersonic wind tunnels. Looks like this. If you're interested, you can visit our labs. Maybe you already did. There are across the street aerodynamics laboratories. We have a low-speed wind tunnel, which is a leegwaterstraat, but the rest of the wind tunnels are over here. 2 supersonic wind tunnels and a hypersonic wind tunnel. And also there we have an open jet wind tunnel for really low-speed research around wind turbines. This is our hypersonic test facility, where we have, it's a Ludwig tube type. We have 2 small pressure vessels where we heat up the flow because it's expanding and cooling when it speeds up. Heat up the flow and put it under high pressure. And then we open the valve, which is down there. It goes through, so here are the tubes. It goes through the tubes. Here's the test section where we perform the test. It's about this size. And then you can measure for about a millisecond before the flow really, what do you call it, vaporizes. So here we perform research, for example, on re-entry vehicles. We have a research project on, for example, the form of the nose of a re-entry vehicle and looking at the temperature distribution. And if you change the design of the nose, how it changes the temperature distribution along your re-entry vehicle. So that's our hypersonic test facility. Okay. So an overview of supersonic wind tunnels. So way up here there's a reservoir with reservoir conditions. Conditions are such that the pressure ratio over this and the contraction ratio of the nozzle are such that you can get supersonic flow. So then before the throat you have subsonic flow. The flow speeds up isentropically, Mach 1 at the throat, and then the flow speed increases. So once you have supersonic conditions, it is the other way around. So if you increase the area for supersonic flows, the flow expands and the density changes such that your flow speed goes up, actually. And then you have supersonic flow here behind the throat. And here's typically your test section. Of course, if the flow speed has to slow down again to subsonic flow, there it goes with a shock. And then you cannot apply isentropic flow relations anymore. And here you see a rocket engine, and that's similar. Just a slightly different design, but again, high contraction, high pressure, high temperature, subsonic flow before the throat, M is 1 in the throat, and the Mach number is higher than 1 after. Now it's a bit intriguing, right? Why is the Mach number 1 in the throat? And why is this the other way around? So for supersonic flow, please, if your area goes up, your speed goes up as well. Well, there's a sort of indicative analysis in Anderson I want to share with you to show you how you can get an idea about that. And there we start from mass conservation. For compressible flow, so rho VA is constant. And then to get them a bit separate, we perform a trick, and we take the natural logarithm. So we say, okay, so this one we can do the natural logarithm of rho VA is equal to the natural logarithm of the constant. Oops. Right? You can do that. And then you have to realize that ln rho VA is the same as ln rho plus ln A plus ln V is equal to ln constant. So density, area, speed. Now I take the differential, so I differentiate. Differential of ln is 1 over, so I get on the left-hand side d rho over rho plus dA over A plus dV over V. And the differential of a constant is 0, so that's actually equal to 0. So I can rewrite my mass conservation. I wouldn't recommend it in general. For this purpose, I'm working my way towards something in this form as well. Now we have d rho's, so changes in density, dA's, changes in area, dV, changes in velocity. So if in some way we can get rid of these changes of density, we have in a way how area is related to velocities, right? So that's what we're looking for. Changes in area in the throat, it's sort of the minimum, so it's 0, and it's increasing or decreasing. It would be nice if we can see then if the speed is increasing and decreasing. So we're looking to get a way to get rid of this d rho. And a nice candidate might be the speed of sound, right? And the speed of sound was dp over d rho, was the speed of sound squared. So if we can eliminate this d rho for the speed of sound, maybe we can get a relation relating areas to speeds and speeds of sound, so Mach numbers. So let's see. The first thing we do to do this is use the Euler equation. Compressible flow relation again. Of course, we cannot use the incompressible flow here because we also would like to go to transonic and supersonic flow. And the Euler equation is dP is minus rho v dv. And please note it's capital V, so this is speed, velocity. And we also have, of course, the relation A squared. So we have A squared is dP over d rho. Now the first thing we do is put in the, well, we do actually both. So we put in the dP and we put in this one. So first thing we do is we realize that d rho over dP is 1 over A squared, right? Because A squared is dP over d rho. So if we have the d rho, so we have that d rho is equal to dp over a squared, right? And dp is equal to minus rho v dv. So if you put that in, you get this one. We have then the, so, well, let's do it like this. So the d rho is equal to dp over a squared. A squared rho, right? So then the dp is minus rho v dv. So we have minus rho v dv on top. Minus rho v dv on top. Divided by a squared over rho. Rho drops out. So we have minus v dv over a squared, right? So putting in the a squared equation and the Euler equation, we can replace d rho over rho by minus v dv over a squared. So this is nice. Now we have only dv's, so changes in velocity, and da's, changes of area. And we have this small a squared, and that is of course the speed of sound. Sometimes it's also denoted by c. But I think Anderson uses a, so I stick with a. Okay, now we collect all the dv's on one side and all the da's on the other side. So we have dA over a on this side, so we take the dv over v minus v dv over a squared to the other side. Sorry, that step was not done, so we do. So one intermediate step. So dA over A is equal to dV over, dV, and then this one becomes plus, so we have VA, different A, V over A squared, plus, and then this one becomes minus, so minus 1 over V plus VdA. So if we multiply this by V, we get then V squared, and we divide by V here again, right? So we multiply by V over V, put one V inside and one V below. Then we have here minus 1, and we have here max squared. Yeah? So dA over A is minus 1, or max squared minus 1 dV over V. So here we are. No? Yes, I can go back one. So what did I do? I took all the V's to the other side. So I had then V over A squared minus 1 over V, right? Then I multiply by V. So you get V squared over A squared, and here minus V over V. And then of course I have to divide by V here as well. So I get dA over A relating dV over V. And what I get here in between brackets, this one is minus 1, and this one is plus max squared. So max squared minus 1. So this is an area velocity relation. Here I stop with the differentials, and what does it say? So if I know something about my changes in area, I know the Mach number, I can find the changes in velocity, or the other way around. Now suppose, let's first consider subsonic flow, right? Subsonic flow, so Mach is smaller than 1. Yeah? So Mach squared minus 1 is smaller than 0. Negative. So for subsonic flow, this bit is negative. So that means if dA is positive, dV is negative, right? Because plus is minus times minus. Yeah? So if dA is positive, what does it mean? My area goes up. So for me, let's see, you go from left to right. So my area increases, right? So I get a larger area if my dA is positive. This one's negative, so my velocity decreases. So this tells you that for subsonic flow, if the area increases, your velocity decreases. The other way around, if the area decreases, so if dA is negative, so it changes negatively, it becomes smaller. This is negative, so then your velocity becomes larger. So if your area becomes smaller, your velocity becomes larger. That is correct, right? Even for low speed flow, we have V times A is constant. So if V goes up, A goes down, and the other way around. So that we knew sort of. Now let's do the supersonic flow. So Mach number for supersonic flow, Mach number is larger than 1. So m squared minus 1 is what is m squared minus 1? Is the Mach is larger than 1? Larger than 0. Positive. Perfect. So for supersonic flow, it's entirely the opposite. If my dA is positive, so dA is positive, so my area increases, right? This case, so my change in area has a positive sign. So this one's positive, this one was positive, then dV is positive too. So then, for supersonic flow, area increase, speed increase. And of course, area decrease, this one's still positive, speed decrease. So in this case, the speed will go up for supersonic flow, and in this case, the speed will go down for supersonic flow. Yeah? Clear? Now, what happens if m is 1? So that is the throat. Indeed, m is 1, m squared minus 1 is 0. So then dA is equal to 0 times dV. So my dA is at the minimum, 0. Right? You can also show it, Anderson has a sort of harder way to manipulate this. You can also play around a bit. So you can say I rewrite it. dV over V, this is the way it is in Anderson, is equal to, you take this to the other side, 1 over Mach squared minus 1 times dA over A, and then you have division by 0. So you have a problem, so you should see what is happening. So this one then goes to infinity, then dA over A has to be 0. So you get dA over A equal to 0 is the only way to keep dV over V finite. So in the throat, Mach is 1. This is not very rigorous analysis, but this gives you an idea. So what did we do? We started off a bit strange. We started off with rho VA is constant to get the area in there, mass conservation. We took this ln thing, differentiate to find area changes. We used the Euler equation and the relation for the speed of sound, and through that we got this area velocity relation. And this might help you to see that what is going on. I personally still find it hard to understand, especially for sonic and supersonic, what is happening. But this is what is hidden inside the physics. Okay. So if you make a plot of your nozzle flow, you can plot then for supersonic flow the Mach number. Now with supersonic flow, the Mach number in the reservoir, you start in the reservoir, so 0. Your flow increases isentropically until the throat, and this is then the throat, right? Mach is 1. And then if your area still increases for isentropic flow, your Mach number increases as well. Now, what does your, and this is all still isentropically. So what does your ratios, what do the ratios look like? T over T0 starts at 1 in the reservoir, right? T0 over T0 is 1. And that one decreases. Pressure decreases ratio, and density ratio decreases. So this is the way these ratios look like inside a supersonic nozzle. Then one thing that is there's a section on in Anderson on measurements of supersonic flows, and that is a whole different ball game. You don't need to know this. Anderson poses a relation that you can use for supersonic flow measurements, but it's way too advanced for the exam. What actually happens in supersonic flow, so if you have a rocket or some object inside supersonic flow, the presence of this object, so you have supersonic flow coming at it here, so Mach larger than 1. The presence of this object is communicated throughout the flow by the speed of sound. So there are sound waves going out, so through the speed of sound, and these sound waves, if you draw them at different instances, they collide at a certain, depending on the Mach number and depending on your geometry, in a shock, so at a certain position. So once you have an object inside your inside supersonic flow, you get a shock, and quite often a shock wave around or even sometimes in front of your measurement thing. So if you put a pitot tube, do I have a picture? No. So if you have a pitot tube inside your supersonic flow, you might even have a shock here. So then you don't measure actually what is going on here in your supersonic flow, but you disturb your flow such that you have a problem. So we use different ways to measure supersonic flows. So that's not on that more in the compressible aerodynamics class next year. Okay, then I finish with a few homework examples you can exercise at the end of the Anderson, 4.8, 4.10 and 4.24, playing around with these compressible flow relations, isentropic flow relations, number 1, number 2, and the energy equation. It is, I think, costs you half an hour or an hour in the weekend, but it gives you an idea on how well you can do that. Then the instruction on this section is next week. So next week you will do a compressible flow in the instructions as well. But it might be good to practice this in front so you're really well prepared. Please be aware the answers, so not the derivations, but the answers are in the back of your book, right? Of the even homework examples. Any questions? Okay, then see you after the break. Got a few questions in the break that were good questions I would like to share with everybody. One was on this exam question where I skipped a step because I prepared slightly different. Of course, here we have computed the ratio of the density, the total density over the density in the throat, but you don't have the total density yet. So what you needed to do here is, can we go back one slide? Oh, I hate that. Terrible, sorry. That's why I prefer the blackboards. So here, sorry. So what you needed to do is, of course, apply the equation of state, right? So the equation of state, so with the rho 0, you can directly compute we have a P0 and a T0. So P is rho RT. Yeah? Okay. Okay. So that brings us to the actual topic of this lecture, viscous flows. So far, all the relations we derived, please. Hello? Please. Okay, so far all the relations we derived Come on. If you would like to talk, please go outside. It's perfectly fine. Leave now and let the guys who want to listen to me listen. This takes 5 to 10 minutes out of 45 minutes because I have to wait before everybody's quiet. I mean, it's fine if you're 8 years old, but not 18 or older. Come on. This is perfectly, you're liberal to do whatever you want, but don't obstruct us. Okay. So far all the relations we derived are valid for inviscid flows, right? We assumed isentropic flow, so reversible flow, so no friction or dissipative effects. With Bernoulli, we derived it from a pressure force balance over an element, a fluid element, and there we also neglected viscous effects. So now a small lecture on what happens inside viscous flows. It's a bit, or it's quite a complex stuff, and you need boundary layer equations, partial differential equations to truly know what is happening. You get a bit on that in the second year, but most of it is actually taught in our masters. So the Masters of Aerodynamics and Wind Energy, if you choose that one, you get really insight into viscous flows. What is done here is I follow Anderson, giving you a few relations and a few concepts. What you need to take from this to the exam and to your sort of the knowledge for this year is definition of a few concepts. What is a separation point? What is transition? What is the Reynolds number? What is a boundary layer? And some idea on how we compute friction drag, because that is what dissipation does to your aircraft, friction drag, and have a concept of pressure drag to be able to apply it. So not too much of equations and trying out things. I'll give you some relations, manipulate them to show you how you can look at drag, but quite different from so far what we did with inviscid flows. And what is relevant there, if you think about viscosity, the first question people ask, is it a laminar flow or a turbulent flow? I'll tell you about what it is and how they transit, so how one can change into the other. And people quite famous for their contribution to viscous flow theory are Osborne Reynolds, who introduced the Reynolds number, and Ludwig Prandtl. And it's 4:15 till the end of chapter 4. So today, I hope today, I'll finish chapter 4. So next lecture, then we can continue with chapter 5. So topics of today, viscous flows, of course, laminar boundary layers, turbulent boundary layers, transition, and separation. And quite often people mix up transition and separation, so please be aware. It is quite a different concept. They have a certain relation, but it's quite different. So viscous flows, what are they? Well, a viscous flow has quite different topology than inviscid flow. Suppose we put a cylinder inside an inviscid flow. Of course, inviscid flows, truly inviscid, do not exist. There's always a small contribution of viscosity, but suppose, sort of as a thought experiment, what would the flow then do? It would flow perfectly around it and sort of be perfectly symmetrical and attach here again and continue like this. Well, if you've ever put some object in happening, right? What happens is you get a certain dead water region behind with large vortices here, and the flow, the sort of smooth flow, will at some point, depends a bit on the conditions, but at some point here go straight on. And that we call separate. So this is a fully attached flow. It follows nicely the object, fully attached, but here the flow separates. Well, why does it separate? And what happens behind? The result of this, so the result that you have here a dead water region and here a flow pushing is a force, right? So in this case we have over this object invisibly a perfectly nice symmetric situation here and here. In this case not. So the flow is here pushing the cylinder in that direction, and behind we have this dead water region which is not pushing back. So as a result there is a friction. As a result of friction, there is a force, a drag force in that direction. And this drag force has a contribution due to the pressure difference over this object, so that because the pressure here is lower than here, so that's called pressure drag. And there is friction on the cylinder because the flow goes over the object of the cylinder and it hits it. The flow speed is 0 at the object. Above there is a certain speed, so there's a friction force in the object. So that also has a certain force contribution, mainly in that direction. So this drag is friction and pressure drag. And it depends on the form of your object, conditions of the flow, which one is dominant. In this case, pressure drag is dominant. Friction, the fact that there's some friction here on the surface is almost negligible compared to the pressure difference. That's the result of this drag. And of course, suppose that this is an aircraft, you try to fly forward, so push in that direction, or you want to keep it here if you have a flow coming, then this drag is working the opposite. So to keep it, if you let this loose, your cylinder will go in that direction, right? So you really have to keep it there. So that's why you need the engines. Okay, so viscous flows, always viscosity plays a role, depends a bit. In liquids and for small objects it's much more dominant. So airflow around very small objects, air around a fruit fly is as if a bird tries to swim through oil. So you can have certain numbers that relate how you can compare flows, but for each object you have a friction somewhere. For aircraft flying through air at high speeds, this friction location is the area where it has an effect is usually only in the boundary layer. But if you get separated flow, so if you put your aircraft at a very high angle of attack, your flow separates off your wing, you get a larger portion where friction is non-negligible. Because of course, this whole thing is due to the effect of friction. If you have an airfoil like this at a high angle of attack, you get a very similar flow pattern. And then of course, you cannot neglect friction in this area. So the whole topology is due to the friction. But right at the surface velocity is 0, whatever happens, also at thin boundary layers. Now, here a picture of an airfoil at a very low angle of attack in a flow. Now, you see here the boundary layer sketched, and you see that the boundary layer grows. So here at the leading edge, the boundary layer is 0, and it grows along the length of the airfoil or plate or whatever. Now we don't have separated flow, so suppose we have attached flow, then we have this boundary layer here growing and we have a friction force due to the fact that we have this boundary layer. And inside the boundary layer, outside the boundary layer, the flow goes with sort of the flow that it would have if you don't take into account friction. And inside the boundary layer, very thin layer, the flow is decreasing, so from quite a fast speed outside to 0. And that is really the origin for the friction flow. What does the pressure do? Well, throughout the boundary layer, so in normal direction, if you have these thin boundary layers, the pressure remains constant. So if you look at pressures, you can assume this flow to be frictionless and not look at the boundary layer. But of course, if you want to know the friction force, you need to look at it. And the thickness here is quite exaggerated, and in reality it's much smaller. So the pressure perpendicular to the surface throughout the boundary layer is non-changing, it's constant. Okay, so now what are we interested in? We're interested, of course, in the friction force on our aircraft. And we're interested in the thickness of the boundary layer, what happens. And it depends on your type of flow, actually. Please be aware that outside the boundary layer, you can assume inviscid flows for attached flow. But inside the boundary layer, it's really friction that's driving all the effects. So you cannot apply Bernoulli. And you cannot apply isentropic flow relations either, because it's really irreversible. Friction is a process where kinetic energy, speed, is transmitted into temperature. So you have temperature increase. At aircraft, it's not so important, but at, for example, re-entry vehicles, it's quite crucial. So now a plot of what happens inside this boundary layer. So suppose here we have our outer flow. Here we have our object, so the surface of our airfoil or flat plate. And this is then the speed. So the speed decreases from the outer area speed to 0, like this. And the boundary layer thickness is the thickness of the area in which this happens. So quite often it's hard to say it exactly, but we report that sort of 99% of the outer flow is recovered inside the boundary layer. And we denote the boundary layer thickness with delta. Now, what causes this friction? The friction is caused, so suppose this layer was like this, so the velocity was much higher close to the object. Would you have a higher friction or lower friction? So suppose, no, the depends on really working. So suppose I have a thicker, I have here a faster velocity closer to the object. So like this, instead of this profile, I have something like this. Do you think the friction would be higher or lower? Who thinks the friction will be higher? You have higher friction? 1, 2, 3, 4. A few hesitants. Lower? Oh, it's the other way around. It's higher. Is this working on this? No. Why? Because the flow has to be decreased in a smaller area, right? So the friction, what does the friction scale with? It's the steepness of this, so the du over di. And y is this in this direction, u is this direction, so the du dy is the steepness of this. The steeper it is, so in a way you should transfer it because you should look from it from this side. So if it's steeper related to this, maybe I'll draw it. So this boundary layer or this boundary layer, this is y, this is u, this is du dy, and in this case du dy, which you should really, so u is like this, right? So du dy, you should put it the other way around. If you normally used as plots like this, right? So then you should turn it around, and then this one is steeper than this one. Yeah? So the u is increasing faster if you go up. So the full boundary layer close to the object has a higher friction force. Now, how is it related? The shear stress, so this is a stress term, and it has the dimensions of pressures. So it's force per surface, so the shear stress on the surface is proportional to the du dy at the surface, at y is 0, and then it is proportional with the mu, and the mu is absolute viscosity coefficient. And for air at standard sea level, it's like this, 1.789, 10 to the minus 5 kilograms per meter second. So quite small. Yeah? Sorry. Yes. Sorry, in the x-axis? In this, what we write here? Okay, so this here, it's a bit confusing because the reality and how you normally plot it. So this, we have here our surface, yeah? So our plate. We have a boundary layer over it. So 0 velocity here, and the velocity is increasing. So this is the distance to the surface. So the velocity, if you look at slightly above, if I blow air over this table, slightly above I have some velocity. Some velocity here, some velocity here, some velocity here. So if I plot this like this, then what I have here is the distance, in a way, what I plot in that direction is distance to the surface, right? Y. What I plot in this direction, so if it is here or here, it is in a way u, the speed. So your normal we're used, but the speed is a function of y. So normally we are used to have the speed as a function of y like this, right? No? That's okay. I draw it like this because it's what it in reality is. But if you should actually turn it around. So then you have the speed at a certain y. You get this. Right? Let's see. U. Well, the only thing you should know is that what you draw here is actually dy over du. Right? So if it is like this, dy over du is smaller, right? But du over dy is higher. That's maybe the way to look at it. Yeah? So important, boundary layer, Reynolds number. And the Reynolds number is a very important dimensionless number. Mr. Reynolds came up with it, and this is a definition. Well, why on earth would he come up with this? So rho Vx over mu. To begin with, these have the same dimensions. So rho Vx has the same dimensions as mu. So rho Vx is kilograms per meter second. And this one's also kilograms per meter second. So this is a dimensionless number. What does it tell you? Rho Vx is convection. So V is your speed, rho is the density, and these are free stream conditions. And this x is the location along your plate or object. So suppose we put a flat plate into a flow, then the boundary layer thickness changes, right, accordingly to x. And also your friction force changes along the sides of along the coordinate of the plate. So this x is the x-coordinate along the plate. So the length over which the flow has flown. So rho Vx is actually sort of related to convection, right? The speed of the flow itself. So convectional phenomena. Below we have the viscosity coefficient. So that is viscous, so diffusion, the dissipation. And Reynolds number tells you how important convection is over diffusion. So suppose we keep the length the same. So suppose we have a plate of 1 meter in air, high speeds, and we keep the viscosity. This is constant for air. So then for high speeds we have a high Reynolds number, right? And for lower speeds we have a low Reynolds number. But we can also look at the length. So what I told you is that a fruit fly, so very small insect, flying at not so high speeds, but through air, very small, has a small Reynolds number. And if you compare that to something large, like an aircraft, right? So suppose he's still flying at the same speed as a fruit fly. Aircraft, it's probably not, but an aircraft is 1,000, 10,000 times as large. So then your Reynolds number would be much larger, so you need much higher viscosity to get down to the same Reynolds number, right? So that's why I say a fruit fly through air, flying through air, has similar same Reynolds number as an aircraft through really, really thick oil. And why is that relevant? Well, if the Reynolds number is constant, you get similar flow phenomena. So similar vortex patterns, similar transition from laminar to turbulent. So the Reynolds number as the Mach number, these two are the crucial dimensionless numbers. Mach number for general flows, Reynolds number for viscous flows. And we sometimes use also, this is the absolute viscosity coefficient. This is the kinematic viscosity coefficient nu. So that's the Greek symbol nu. And the definition is mu over rho. So, I prefer to keep it like this, but sometimes people work it into this. Now there are two types of flow and a transition through it, laminar flow and turbulent flow. And when it undergoes transition depends on the Reynolds number. At the critical Reynolds number, the flow will go from laminar to turbulent. And what is laminar and what is turbulent? Well, I showed you the picture of the smoke, flow with smoke over an airfoil. Laminar flow, it's all smooth, streamlined. Turbulent flow, small perturbations are there and are growing, and you get very small vortices in all kinds of directions. So no smooth flow, but the streamlines break up. And you get a sort of random flow. Of course, the general flow pattern is still like this, but locally you get very small vortices, which have an effect on the friction and on separation. More about that later. Now, laminar flow. There's boundary layer theory for flat plates, and from that, the real theory you can get from us in the 4th year, but from that, you can derive a boundary layer thickness equation. This is for flat plates, and it tells you that delta, the thickness of a boundary layer at a certain location x, is equal to 5.2x over square root of Reynolds x. Now, please be aware, Reynolds x was rho Vx over mu, right? So suppose we keep rho V and mu constant, the rho infinity, V infinity, so that's the free stream conditions. So here's square root of x. So we have x over square root of x. So how does that behave itself? As square root. So the boundary layer thickness in laminar flow grows as a square root function. So it's parabolic, right? Proportional to square root of x. So in the beginning it will grow fast, and later it will grow less. Now what we're interested in is the friction drag on this flat plate. So the friction drag depends on this friction shear stress, where we have a relation from laminar boundary layer theory. I'll give it in a minute. And that friction force changes, so the shear stress changes along the plate. The shear stress at the leading edge is different from the shear stress at the trailing edge. So what do I need to do? I divide my plate into small strips. On each strip, so I have flow from this direction. It has a unit width of 1. So nothing is happening in this direction. So everything is happening in this direction. So I divide my plates into small strips like this at location x. And I have to integrate then from 0 to L the shear stress on these strips to find the total friction force. And the total force is, of course, a sum of the total pressure force. But if it is really horizontal, we have friction force. So we'll now look at the total friction force. How do we compute the total friction force on this element? Stress, that was force per surface area, right? Per unit area, like pressure, has the same dimension. So newtons per meter squared. So to get from newtons per meter squared to newtons, we have to multiply by meter squared, integrate. So we integrate the shear stress, tau, times the area of the strip. And that is the length 1 and dx, so 1 times dx. So the shear stress here is tau, times the area gives us the friction force. So the local friction force on this element is tau times dx. Now if we want to have the drag, we integrate from 0 to L this local shear stress times dx from 0 to L, right? Okay. Yeah. This is a bit I like least. What you need to know from this really is concepts and how you would approach this. So concepts, laminar flow, turbulent flow, shear stress, friction drag, pressure drag. But because we don't have really the tools to do the nice analysis. So skin friction coefficient. So this shear stress that we're interested in, again from laminar boundary layer theory, there is a relation relating this shear stress to Reynolds x again. So this shear stress is different at each location. And it differs like this. And that's usually given again in dimensionless form. So we don't give the shear stress directly, but we give this friction coefficient, the skin friction coefficient. And that's a dimensionless skin friction, and it's equal to the shear stress divided by the dynamic pressure, half rho v squared. So tau w over, you can write this q infinity. And then from laminar boundary layer theory, we know that it's 0.664 over square root of Reynolds x. what does this tell you? Is the shear stress larger at the leading edge of the plate or at the trailing edge of the plate? Who votes for the leading edge of the plate? For small delta, for small x? Do we have small x have a large friction force? Who votes? Who says no, small at the beginning of the plate? Okay, well, only 10% voted, but it's about half-half. We divide over x, right? Over square root of x. So if you divide by a large number, it's small. And if you divide by a small number, it's large. So at the end of the plate, it's much more smaller than at the beginning of the plate. So this has to do with the growth of your boundary layer thickness, actually. So CF and tau W decrease as square root of x increases. Yeah? Okay. Now, what we were doing, we are calculating the friction force. No? Questions? Remarks? Problems? No? Okay. Then I'll continue. So we're integrating tau W from 0 to L. Then I go faster. Apparently you're bored. So tau W is, you can give CF times square root of Reynolds x over 664. So that we do. We find the drag. We integrate our tau W, and that's the same as the friction coefficient times Q, right? Because this was dimensionless, so times the dynamic pressure. Then from the previous relation, from laminar boundary layer theory, we know that this is 0.664. We have the Q, but that doesn't depend on x, over square root of Reynolds x. So here we have our 1 over square root of Reynolds x. To integrate this, we separate it into everything that's with x, 1 over square root of x, and all the other thing we take outside. Now, primitive of value of 1 over square root of x, so x to the minus a half. Here it is. So this is x to the minus a half. So if you take the differential of 2x to the power a half, you have 1x to the minus a half. So the primitive value we're looking for is 2 times square root x. So we have to take that between 0 and L. In 0 it's 0 and in L it's L, so it's 2 square root L, right? There, and everything that was before. So we have to multiply the 0.664 by 2, 1.328. We have our Q infinity, and then we have here square root of L, and what I do, I have here the remains of my Reynolds number, but it would, so square root of Reynolds number only without the L. This is my kinematic viscosity coefficient, so rho over mu. So what I do is write square root of L as L divided by square root of L, right? So then I have here a Reynolds L and here L. So my drag force is 1.328 Q infinity L over square root of Reynolds L. So it depends very much on the length and on the Reynolds number, what the skin friction is, right? Please be aware, this is only on one side of the plate. So if you put the plate like, if you have flow over a plate, this is fine. But if you put the plate like this and you have flow on top and below, you need to multiply it by 2 for the top and the bottom, right? Now, we normally don't like forces, but we like force coefficients. So we usually work with lift, but lift coefficients. Drag coefficients. So what do? We make the force dimensionless. So we work here with the skin friction drag. So this is a capital C, different from that small c. So that is the dimensionless drag. And how do we make it dimensionless? By dividing by Q times S. So as we do with lift forces, we do with drag forces. So we divide the drag over Q infinity times S. So this is the dynamic pressure times area, so that is a force as well. So that is a typical force for your flow. So this skin friction drag coefficient is then this one divided by Q infinity S. Well, Q infinity drops out. What is the area of our plate? That is L times 1. So we divide by L. So then we have this one. So L, S, we divide, the L drops out, so we end up with this one, 1.328 without the Q and infinity and the L over square root Reynolds L. So you see that the Reynolds number determines not only the thickness of your boundary layer, but also the friction. So high Reynolds number, if we put the plate in a high Reynolds number, so high Reynolds number, we have a thin boundary layer, right? So that was laminar flow. Now for turbulent flow, we have similar relations. Why is that relevant? Well, what is turbulent flow? Flow transits at some point, goes from laminar to turbulent flow. How does that happen? Suppose you have very high speed, so a very thin boundary layer. Every wing is a bit dirty, right? You have small spots of dirt on the wing. If your boundary layer is very thin, it hits these dirt things and then is perturbed. It is not smooth anymore, but these small eddies start. So then you get already transition to turbulent flow. And you get that for high speeds, high Reynolds numbers, much faster than for low. Now, turbulent flow question. Sorry? Yes, I'll come to that. So indeed, a turbulent flow has higher friction, but it has, so there it's less good, you would say, but it has favorable characteristics for a stall flow, so for a separation. I will come to that. I hope I'll make it. So turbulent flow, these relations don't even come from laminar boundary layer theory, but experiments. And the one thing to take away from this is that the boundary layer thickness is not a function of square root of Reynolds x over square root of Reynolds x, but it's Reynolds x to the 0.2. So we divide by something that is smaller, right? Not 0.5, but 0.2. So we divide by something that's smaller, so the overall is larger. So if you would plot a turbulent boundary layer on this plate and a laminar boundary layer, the turbulent boundary layer would be thicker. After transition, you get a thicker boundary layer because of all these small eddies. And you can actually, do I have a picture? Here, yeah. A very nice picture of transition from laminar to turbulent is smoke from a cigarette. Laminar, 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 turbulent. Yeah? And then also skin friction drag coefficient is, you can do a similar trick as we did just now. Scales with not Reynolds L to a half, but 0.2. Now please note, turbulent boundary layer is thicker, right? This is larger. For the same Reynolds number, a turbulent boundary layer, again, is dividing by Reynolds L to the 0.2. While laminar, you had Reynolds L to the power 0.5. So we divide by something smaller, so it's higher. So the friction and the friction drag of turbulent flow is higher. Why? Due to all these eddies in all directions, they also have they grab the object more. They have more energy in all directions. Yes? Sorry? Well, I defined Reynolds x. Well, if you substitute the length of the plate, so the end plate, I'm integrating from 0 to L. So I'm looking at the drag on a plate of length L. Yeah? So that's Reynolds at the end of the plate. Normally, you can talk also about a characteristic Reynolds number for a flow, and quite often you look at the chord. So the Reynolds, you fill in the characteristic length that determines your flow. So it's then the chord length. So this is Mr. Reynolds, who did a very nice experiment showing transition in a water tunnel with dye. And there you can again see that after a certain Reynolds number, so for low Reynolds number, you have smooth flow throughout your pipe. If you increase your Reynolds number at certain points, you have transition to turbulent flow. And this is at a certain point where the critical Reynolds number is reached. Now, what does that mean for your friction drag coefficient? Well, we just showed that it is a function of Reynolds number for laminar. For turbulent flow, it's higher. What happens if the flow transition, you go from this path to that path? So this is actually from experiments. Now what does it look like? If you look at, for example, the way we do this, we put oil on the surface. And through oil on the surface, you can actually see what's happening on the surface. Well, laminar flow has a very smooth surface streaks. But if you look along the plate, when it's transition to turbulence, you get these structures. So flow over a plate starts off laminar, but at a critical Reynolds number, through the Tolmin-Schlichting waves, again more on this later, you get the vortex breakdown, small perturbations grow, and you get transition into turbulence. First turbulent spots and then larger eddies. And Ludwig Prandtl also is quite important. He derived the boundary layer theory that we are using the results of. Now let's look again at our boundary layer. A laminar boundary layer, that's the red one, looks like this. It's not so thick. Up here you have the free stream velocity, but it's not very full here. While the turbulent boundary layer is thicker, so it takes longer before you have the free stream velocity. But due to all these eddies close to the object here, it is much fuller. So here you can already see that indeed skin friction is higher for turbulent flow, right? Because this one is less steep. Now how does it look if you look at the boundary layer? Thickness, laminar flow, transition to turbulence, and then a thicker boundary layer. Now when does this happen? At a certain Reynolds critical. So you need to know the definition of laminar flow, or the concept of turbulent flow, and the definition of the critical Reynolds number. And the critical Reynolds number is the Reynolds number at which you have transition from laminar to turbulence. Typically found from experiments, but then you can use it, right? And the Reynolds number is depending on x, so on the coordinate of your plate. So here it's smaller and it's increasing. And here it has reached a certain critical value, and then you have transition to turbulent flow. So on similar concept, of course, on flow around an airfoil or wing, laminar flow, transition point, turbulent flow. And it depends on the conditions. Your transition point can be anywhere. For gliders, so for really low speed aircraft, they design that to have as low friction drag as possible. So to have laminar flow, and they manage to have laminar flow up to 95% of the wing. While for commercial, we have to go home. No, it's gone back. For commercial transport aircraft, the Reynolds number is much higher. You're flying at higher speeds. The length might be, the chord length might be longer. And then it's very hard to have laminar flow for such a long portion. Typically you have transition around half of the chord or even before. This is a picture of our wind tunnel, an experiment of a blade in our wind tunnel. There you see the transition very well. So the flow is coming from this side, oil pattern on the object, laminar flow, turbulent flow. It depends what you look at, but if you look at the skin friction drag or the shear stress, then laminar flow is favorable, right? So the shear stress of laminar flow is smaller than that of turbulent. And here you see a design of a glider airfoil, which is 95% laminar flow. But normally, the vast majority of flows is turbulent, especially in aerospace. Now the next concept, so this is laminar turbulence and transition. Now we move to a different concept that flows can do, separate. And this is also a viscous effect. So if you have viscosity in your flow, small changes locally can make your flow to separate. Why does it separate? Well, it is separating because it's fighting a positive pressure gradient. So the pressure is increasing and increasing and increasing. At some point it says, I'm not fighting the pressure anymore, I just go straight on. So the flow is not attached anymore but separated. And here you see it with dye around the circular cylinder and how it starts. So small vortices grow and you get a large dead water region here. Now, why is it important and when does it occur? For an airfoil at zero angle of attack, of course the flow is fully attached. But if you increase the angle of attack of your wing, at some point, I mean in 90 degrees angle of attack, you have just a bluff body, the flow is fully separated from leading edge to trailing edge. Somewhere in between, separation starts. And indeed this is related to the stall. So the flow stalls, so you get first a small separation bubble, and then the separation moves upwards, and at some point, for a large angle of attack, you get leading edge separation. And how does it look like? Sort of, it is very unsteady phenomena as well. Around the circular cylinder, you get von Karman vortex shedding, so a vortex rotating in that direction, quite a nice flow. And here, again, you see a picture of it around the cylinder. So here, so when is it separating? Well, when you have, the more curvature you have, the stronger the adverse pressure gradient, so the earlier it leaves, the flow leaves the object and separates. So this is called the separation point, so where the flow separates. First you have normal flow like this, and here you have your separation point. And in this case we have actually leading edge separation. This is one of the first experiments by Van Dijk. Aluminum powder in water, and you can see this is called the dividing streamline, dividing the outer flow from the dead water region. Now how can you tell separation, what is it doing to your pressure and your lift? So this is attached flow. Small angle of attack, airfoil. Then we have the red, a few more minutes, red pressure gradients. If you increase the angle of attack, you get at some point separation, and then your pressure gradient drops. And this is really trailing edge separated, so you can get really very bad pressure distribution if it's fully separated. And separation you can see in the flat pressure coefficients, pressure gradients. So example, the Nando Timmer, who's teaching the Dutch class, is a wind turbine expert, wind turbine aerodynamicist, and he designed wind turbine airfoils. And this is an example of the wind turbine airfoil designed at, here at Delft, DUW91. This is the pressure contour at zero angle of attack. And now we increase the angle of attack, 26, 5.6, 7.2. Where do we have separation? Separation is a horizontal line in the CP. So here at the 90.2 degrees, you see there's a small separated area at the trailing edge. And if you continue, 18.2, so very high angle of attack, you get the separation point here. So the separation point moves upwards. And it can really be quickly. So for example, it can start as a small bubble, but after a certain angle of attack, it just springs open and moves to a leading edge separation. That's why it's such a non-linear behavior. So in next chapter, when we look at chapter 5, airfoils and wings, we see what it does really to your lift and airfoil. Now one more concept, 1 minute. 1 minute. So what does turbulent flow do to separation? Any idea? Will turbulent flow separate earlier or later? Who votes for earlier? Earlier separation? Who votes for later separation? Ah, the minority has it right. Yeah. I'll show you a picture. This is a very nice picture that can illustrate it. Turbulent flow has all these small eddies, so it has energy in all directions. So it has more energy to fight the adverse pressure gradient. So although turbulent flow has higher friction, it has later separation. So here you see a ball with no turbulent flow, so laminar, very smooth edge, and then the flow separates here. Here I put now a strip to make transition to turbulence earlier, to disturb it. We call it a transition strip. Look what happens to the separation point. It moves much way down. So for separation, turbulent flow is better, right? Any questions? No. Oh, yeah. Sorry. Maybe come here, because I don't think I can hold them here. Thanks.
Please visit our OpenCourseWare website for more information. See you at our next